Okay, I'm just going to pick out a few problems that some kids had some questions about so that you guys that have been gone can kind of get an idea of kind of if you're doing this correctly or not. Let's pick a few out of the book, like, let's see here. Seems like 10 was tricky for some folks because it didn't have numbers, it just had letters, and that's okay. You're going to do 10 just like you would have done 9, but all you have are letters. So it says that to find the length and width of a rectangle that has the given perimeter, and the perimeter, they're just calling it P, according to the book. And you know perimeter is 2 times width plus 2 times length, and they want a maximum area. And something I told the kids today, it's length times width, is that you look at the sentence that has the word maximum or minimum, and that tells you which equation you're going to find the derivative of. They want the maximum area, so this is the equation that I'm going to derive, which means this equation I need to rearrange and get one of these two variables by itself so that I can plug it in here. Now remember, typically this is going to be a number over here on the left, but all they give you is P. So we're going to keep in mind that P is a constant. I'm just going to solve this thing for, I don't know, W, I guess. So I have P minus 2 times L equals 2W. So W is going to be P minus 2L all over W. Whoops, all over 2. Goodness gracious. Here we go. So I'm going to replace W with this little guy right here. So that I have area equals length times what we know W is, which is P minus 2L all divided by 2. I'm going to clean this up a little bit so that it's something I can derive. I'm going to have L times P. Actually, I'm going to put the P in the front because I know that's actually a constant. Minus 2L squared, and it's all over 2. And now I'm going to make this a little easier to do the derivative, I'm just going to separate this into two different terms so that I have 1/2 P times L, or P over 2 times L, same thing, minus these 2's are going to cancel, and I just have L squared. Now that's something that's pretty easy to derive. So we say, okay, derivative, remember this right here is the constant. If you just had a constant like 3L, it would be 3. So we're just going to put 1/2 P. Minus, you know that that's going to be 2L. And there's our derivative. And to find our maximum, we have to find a critical number, so we're going to set it equal to 0. And now I'm going to try to get L by itself so that I can sort of isolate and find out what length is going to provide the maximum area. So we say negative 2L equals negative 1/2 P. Divide both sides by negative 2 and you get 1/4 P. So that's what our L is. You could put it on a little number line. And this was tricky for some kids too because they were like, well, I don't have any numbers to plug in, so how do I know what to do? Well, something you know that is absolutely smaller than 1/4 P, you could plug in a 0 and see what happens. So if I put a 0 in here for L, because that's what we solved for, put a 0 in for L, it's going to be some sort of positive number minus nothing. And a number that's larger than 1/4 P that you can plug in, well, you could put P, because you know that 1/4 of P is smaller than P itself. So we take P and plug it in here. 1/2 of P minus 2P, that's going to be a negative number. So we can see increasing, decreasing, so this must be where our maximum is. So the length is going to be 1/4 the perimeter. Now we need to solve to find the width because I think it's asking, it's asking you for the dimensions. So I'm going to take 1/4 of P and I'm going to plug it back in up here for area. So if L is, actually, you know what, I'm solving for W, so I'm going to plug it in over here. P minus 2 times L, and L is 1/4 P, all over 2, and that's supposed to get me W. So I have P minus, that's going to be 1/2 P, all over 2 equals W. 1P minus 1/2 of P is 1/2 P. And I'm dividing by 2, which is the same thing as multiplying by 1/2. So I get 1/4 of P also is W. And that's the thing about a bunch of these rectangle problems that they give you. If you're maximizing area, you typically wind up making a square. So usually L and W wind up kind of being the same on a lot of these problems. So there's 10. That was tricky for a lot of kids today. What else was tricky? They asked about 14. Several of them asked about 14. And they give you an equation where f at x is x minus 1 the quantity squared. And there's a point out here, negative 5 comma 3. And they're asking about find the point on the graph of the function that's closest to this given point. So here's what's happening is you've got this graph, and we know that it just got shifted to the right one. So we know that the graph kind of looks like that. And over here somewhere we have negative 5 comma 3. They want to know what point on this arm right here on that graph is going to be closest to that point. So we're talking about distance. They want the distance formula here. So we want a minimum distance. We know that distance, actually it's a lowercase d, distance equals the square root of y sub 2 minus y sub 1 the quantity squared plus x sub 2 minus x sub 1 the quantity squared. And because we're minimizing the distance, we want the smallest distance, then this right here is the equation that we're going to derive. So this one's going to get plugged in somewhere. And I can plug a lot of this in. Let's see here. I have this y value and this x value because we have negative 5 and 3. They give us that. And then I've got an x and a y. Well, really, function notation is really fancy for y, so we do have a y. We've got x minus 1 the quantity squared in place of our y value. And now we've got it whittled down to one variable, so we can just kind of play with this a little bit. We've got square root. On the inside, I'm going to have x squared minus 2x plus 1 minus 3 the quantity squared. Plus, I'm going to go ahead and FOIL this out, and I have x squared plus 10x plus 25. And then positive 1 and negative 3, I'm going to replace that with negative 2. And I'm going to need to square that whole thing, so that's not super fun, but we can do it. Let's see here. Yeah, we are going to have to do that. So if I take x squared times everybody here, I'm going to have x to the 4th minus 2x cubed minus 2x squared. And then negative 2x times everybody is going to be negative 2x squared plus 4x plus 4x. Whoops. Not that squared. And then I'm going to take negative 2 times everybody. So I have again negative 2x squared plus, wait, I did something wrong, didn't I? If I take negative 2x times that, I get negative 2x cubed. Negative 2x times that is positive 4x squared, which is what I wrote over here. Goodness gracious, I really messed it up. That's positive 4x. Okay, there we go. So then negative 2 times everybody is negative 2x squared. Positive 4x. Negative 2 times negative 2 is positive 4. So that's just squaring this little piece here. Plus, we've got x squared plus 10x plus 25. So now we put together all of our like terms. Let's see, we've got an x to the 4th. This right here is going to be minus 4x cubed. This right here winds up going away. This is 8x. This is 4. Write the rest and put them together. So I have x to the 4th minus 4x cubed. I have an x squared. I have an 18x. I have a 29. and the whole thing is to the 1/2. And something we can do, hang on a second. Something you can think about is because the distance will be minimized when the stuff that's on the inside is minimized, what we actually can do is we can change this. It's kind of like squaring both sides, because as long as I minimize, if I'm looking for the minimum distance, then I just need the inside to be minimized, and that's going to produce the smallest answer. So if you can kind of square both sides, I guess, and then you don't really have to do anything to that 1/2. You could use implicit differentiation, but there's really no need to, because I can just go ahead and derive this now. The place where this is smallest is the place where this is smallest, so we're going to be okay. I go ahead and do the derivative. And then this is what I'm going to set equal to 0, because I'm looking for a critical number, looking for a minimum value. And I'm just going to use my Poly Smelt program, or you could type it in your y equals button, it doesn't really matter. And I don't have it on this calculator. Just realized that. Okay, well I guess I'll just type it in. 4x cubed minus 12x squared plus 2x plus 18. Oops. I'm going to graph it. It's probably not even on the screen. Oh, kind of. Here we go. Looks like we're crossing at this one point back here, which I'm wondering if that's a -1. Let's see. Yep, it's at -1 exactly. So then we take a value less than -1 and a value greater than -1, and we find out, you know, where it's increasing and decreasing and all of that. Let's see, if we put in, like, say, a 0, that's going to give us a positive. That one's going to give us a negative. Increase, or decreasing, increasing, this tells us that our negative, the smallest distance value is when x equals -1. They want to know the actual point, so it's -1 comma something. To find the something, you can plug it back into the original. So -1 minus 1 is -2. Squared would give you 4. So we have -1 comma 4. And so I believe, let's see, this was 14. I'm going to say there's another one just like it. Yep, 16 is just like it. What else did they ask about on this one? It seems like some kids were confused about the printed page, which I'd like to do one for you that kind of looks like that, because you're going to get one on your assignment that looks like that. I want to make sure you have some guidance. So this is number 18. It says that a rectangular page is to contain 36 square inches of print. So we have a page out of a book, and the print probably only covers up, you know, that kind of space, so that x times y, the length times the width, is supposed to only cover 36. And then they tell us that the margins on all of the sides are 1.5 inches. So we have 1.5 inches going this way and 1.5 inches going this way. So for the entire length of the page, it's going to be x plus 3, because x plus 1.5 plus 1.5. The entire width of the page is going to be y plus 3 for the same reason, because we have 1.5 inches and 1.5 inches over there. So let's see, they say find the dimensions of the page so that the least amount of paper is used. So they want to minimize the area of the page. So if they're minimizing the area, this is the one that we take the derivative of. This is the one that we're going to rearrange so that we have one of the variables by itself. And then we replace it. So we have area equals y plus 3 times x, which is 36 over y, plus 3. And then we're going to go ahead and FOIL. Or I guess we could just take the derivative as it is. It doesn't really matter to me. Actually, let me rewrite this. It's 36y to the -1. I think that'll help some of you guys. You can either FOIL it out and then take the derivative, or you can take the derivative now. It doesn't really matter. I haven't done it like this yet today, but I'll go ahead and do it now. So we have first times the derivative of the second, and the derivative of the second is negative 36y to the negative 2, plus the second times the derivative of the first, which is 1. So now we can start to put things together. I'm going to go ahead and distribute this into both of them so that I have, and I'll do this the long way, negative 36y over y squared, because this is on the bottom. Do you remember that? And then we multiply by a positive 3, and that's going to give us a negative 108 over y squared. And then plus 36 over y plus 3. I can put these, no, I can't put those two together. I thought I could, but I can't. So we have kind of a crazy thing going on here. We want to know kind of where the critical points are, so we need to set this derivative equal to 0, and you could type that in a calculator if you wanted to figure that out, and I think that's what I'm going to do. Well, actually, I'll just put equal to Bazinga! Here's my phone again. Okay. So let's see here. Actually, I think I'm just going to type this right here into my calculator. So that I have y plus 3, just be faster. X plus 3, negative 36, x to the negative 2, plus 36 times x to the negative 1, plus 3. Now it looks like it's going to cross 2 times. We have a negative number and a positive number. I'm only concerned about the positive number because I can't have a negative value when I'm talking about the length or width of something. So I hit second, calc 2, and let's see here. Okay, use, enter. Oops, probably can't see that glare. Enter, enter. Looks like that is 6. Oops. What I was doing. So at 6, there's some sort of critical point. If I plug in a number less than 6, I have to figure out if I'm going to get a positive or a negative for that. And I'm going to, when I plug it in here, 1 plus 3 is 4, that's a positive number. When I plug a 1 in there, I wind up with a positive number, so I wind up with a positive. But I'm pretty sure it's supposed to be a negative. Something's up. 6 over 1. Let's try positive and see what happens here. If I put in, like, say, a 7 or a 10 or something, I'm still going to have a positive, aren't I? Oh, because this is area. Yeah, I need to plug it in here. Yikes. That's where I screwed up. If I plug in a 1 here, that gives me a negative, and this gives me a positive. That makes more sense. So we are decreasing and then increasing, so that there's a minimum value when y or x, whichever one, is 6. We said y. So let's see here. So if y is 6, then the total length of the page is a 9. And if y is 6, then you can tell by looking at this that x is also 6. So we have 6 plus 3 is also 9. So what's going to be best is to do a 9 by 9 page. Does it tell you inches or anything? Yep. It does say inches. So 9 inches by 9 inches is your dimensions. Are your dimensions. Let's see. 20, I know there was a lot of questions on 20. I think it's because they made it too hard. They give you an equation for flow rate, and then it says what speed will maximize the flow rate. Maximize the flow rate. If you're maximizing the flow rate, that means that equation, you just take the derivative of that and find your critical point. So I think they were just making that too hard. I think that's it. I think the rest everybody could figure out eventually. So there's that one, and it's just kind of more the same on your assignment. Good luck.